Another way of getting a better estimate is to use centered rectangles. So what we're going to do here is find an approximation to the area between the same curve, y equals x cubed plus 1, and the x-axis from x equals 1 to x equals 4 by using the rectangles, and they're centered rectangles, shown in the diagram below. Now they're centered because we're taking the height at the center of the interval. So in other words, a 1.5, 2.5 and 3.5. So if we make up a little table of values here, remember all the widths are still 1, then let's use the calculator to do that. So I need to go back to graph and table, and I'm going to generate my table, but this time what I need to do is go up in steps of 0.5, and then at 1.5 I can see I have 4.375, at 2.5 16.625, and also 3.5 is 43.875. And so my area, let's call it area C for area centered, is 4.375 plus 16.625 plus 43.875. And so 4.375 add 16.625 add 43.875 gives me 64.875. Now that's definitely closer even than when we took the average of the left and the right in the last example. And as we said in the last example, the exact area, which we can find by integration, is 66.75 square units. Had we used more rectangles here, we would have got closer. But hopefully you can see the idea with the centered rectangle. We're counting tiny bits of area like this one and this one, and maybe not so tiny bits like that one. We're counting those as part of the area, and we're leaving out these other bits. But that's why it's better than left or right rectangles, because we're both counting some that isn't there and leaving out some that is, instead of just always counting area that isn't there or leaving out bits that are.